All right, let's move on. Let's look at exponential functions. And again, we're going to look at all of the multiple representations of a function beginning with a verbal description. So for an example, you're performing an experiment in science class in which you start with 100 bacteria and the amount of bacteria doubles every hour. This is an example of an exponential function. We still have a starting point. We're starting with 100 bacteria. And in this case, we are actually doubling that number of bacteria every hour. That's important there, that double. That's a keyword. If we look at the numeric table of an exponential function, we still have our independent variables. T in this case is the same thing as x. B of t is the same thing as y, so we have our ordered pairs just like we would in every other table. But in this case, if we go to look at that common difference, we are not adding or subtracting by any specific number every time. That's how we know it is not linear. If I tried to find a common difference of the first terms and know that they're different, and then tried to find the second common difference, and if it was the same, it would be quadratic. That is not the case here. So this is how we know that this would be an exponential function table. We'll come back to that. If we were to look at an exponential function graph, remember in the first video, we talked about the COVID-19 example. And this is a very classic exponential function graph. There's a couple different kinds, but it generally starts with a very slight slope, and then you see a very quick increase or decrease. It's not quite a parabola because this is not a U-shaped graph. I know on the last example we saw half of that parabola, but in this case, this line, if I were to continue to extend it, it would stay pretty close to zero. Let's look at our focus for today, though, because our focus for today is to see what an exponential function looks like as an algebraic equation. So I'm going to give you the following steps to help you learn to write the equation for an exponential function. And the first step is to pick any 2 points. We know we need 2 points to write an equation of any kind of a graph. I want you to always keep in mind the most helpful points that you will be able to use will always be the y-intercept, and it will always be the coordinate where x equals 1. So if we went back, you could go to your graph and you can say, okay, I know well the y-intercept is right here. This is the point where the graph touches the y-axis, but I'm not quite sure what that y value is when x is 0. That's okay because we have a table of values that's representing this graph. So I can go over here and I can say, okay, well, when x is 0, when t is 0, b of t is 100. And when t is 1, b of t is 200. So I'm actually going to go ahead and use those points. And that's where they came from. This one right here is the y-intercept. And this one right here is when x is 1. After you have your 2 points, you will substitute or replace those coordinates into the exponential equation y equals a times b to the x power. Now here's why it's called an exponential function. We are raising the x variable to a power. So let's go ahead and substitute in, okay? If I take this first ordered pair where x is 0 and y is 100, I'm going to take this equation, I'm going to replace y with 100. I don't have anything to replace a with. I don't have anything to replace b with, but I can replace x because I know that x has a value of 0. Now I'm going to solve. If you remember our properties of exponents that we talked about this year, anything raised to the 0 power is 1. So in this case, if I had a times 1, that's just going to give me a, and a is going to equal 100. Perfect. Let's keep going. Now I'm going to take a look at this second ordered pair, and I'm going to go ahead and I'm going to substitute or replace. I'm going to take y out, and I'm going to replace it with 200. I now know A. A is 100. We figured that out. I do not know what B is, but I do know that x in this case, my tiny exponent x, happens to be 1. We got it from this ordered pair. All right, so now anything raised to the power of 1 is itself. So what I need to do is I need to solve this equation, 200 equals 100 times b, and I need to get b by itself. So the opposite of multiplying is dividing. If I divide by 100 on both sides, 200 divided by 100 leaves me with b equals 2. One more step, okay? We need to now substitute a and b into this equation. Y equals a times b to the x power. The value of a we know is 100. The value of b we know is 2. So if I go to rewrite it, I have 100 times 2 to the x power equals y. And that is the equation for this exponential function. All right, so let's practice. I have a couple representations already. I have a numeric table and I have my graph. And I need to be able to write an equation for the exponential function. We're going to use the same steps that we just reviewed. And the first one is we need to pick 2 points. We need to pick the y-intercept and we need to pick the value when x is 1. Okay, so if I go over to my graph, I know that my y-intercept is right here when x is 0. And it seems to be that looking at the intervals that we are counting by 4. To verify, you go over to your table and you say, oh, this ordered pair right here, when x is 0, y is 4. I'm going to use that. I'm also going to go where x is 1, y is 12. I'm going to go ahead and use those ordered pairs. And if you remember the next step, it says I need to go ahead and substitute or replace into the form y equals a times b to the x power. So we're going to use the first ordered pair that we have first. And if I go ahead and I replace, all right, y, my y value is 4. So I'm going to take y out. I'm replacing it with 4. I'm substituting. I don't have a value for a just yet. That's okay. I'm going to solve for a. And I do have a value for x. The value for x is 0. So I'm replacing it. Anything raised to the 0 power is 1. So a times 1 just leaves me with a, and we know a equals 4. Now I need to go ahead and solve for b. And in order to do that, I'm going to use this second ordered pair. All right, so y is 12. So I replaced y with 12. I know the a value, a is 4. So I substituted a with 4. I don't know what b is yet, but I know in this case x is 1. So there's a tiny 1 right there. Anything raised to the power of 1 is itself. So 4 times b equals 12. The opposite of multiplying, what's going to undo multiplication is division. So I'm going to divide by 4. What I do to one side of the equation, I have to do to the other. And 12 divided by 4 is 3. So now I know A and I know B. Okay. The last step is to replace A and B back into this original parent function. So I know A is 4. I'm replacing A with 4. I know B is 3. So the equation for this graph and this table is y equals 4 times 3 to the power of x. So let's talk a minute. Let's form a hypothesis and let's figure out, okay, where this a term, in this case 4, comes from in terms of the graph and the table. What do you think that's representing? If I go over to my table and I'm looking for this 4, it's right here. And that happens when x is 0. It's the y value when x is 0. All right, so if I go over to my to my graph, and I'm looking, that ordered pair is right here. And this point happens to fall on the y-axis. So that makes this my y-intercept. So your A term is the point where your graph crosses the y-axis. It's important that we know that. We also need to know where this B term comes from as it relates to one of the key features of the graph. And we know in this case, B is 3. Well, this 3 right here is just representing when x is 3, my y value is going to be 108. Okay, maybe not that, but let's look. The x values are increasing by 1, and the y values are not increasing by 3 if I'm adding, but if I were adding, it would be a linear function. But I can see that if I did 4 times 3, I'm going to get 12. And if I did 12 times 3, I'm going to get 36. And if I did 36 times 3, I'm going to get 108. And I could keep on going. And what's really important is that if I have an exponential function, I'm not adding or subtracting to find the common difference because that's a linear function. In this case, I'm either going to be multiplying or I'm going to be dividing, and that gives us the common ratio. So A is your y-intercept and B is your common ratio. What I would like for you to do is to try this problem all by yourself. Use the video. If you want to pause it, rewind it, listen to it again. Hopefully you took notes on that as we went through it, but use those steps and try and complete this problem. After you've tried it, go ahead and click on and you can check yourself on the next slide. After you've checked yourself, don't forget to try the exit ticket and submit it.